Hello and welcome back to Introduction to Number Theory. In this video, we'll once again talk about continued fractions and their convergence. So, we have a continued fraction, say a0 plus 1 over a1 plus 1 over, say, and so on, a n minus 1 plus 1 over a n plus 1 over and so on. So this is a continuous fraction. It can be infinite, it can be finite. Mostly we care now about infinite continued fractions, and its convergent is a rational number which can be obtained by taking just a part of this continued fraction. So a convergent that ends with a with index n minus 1 is usually denoted as p n minus 1 over q n minus 1, and the convergent that ends in the next one of a's is denoted, of course, as pn over qn. And now we will study a bit about these two neighbor convergents. What can we say about them? Well, recall that each convergent is equal to continuant of these variables here. Continuant, say, pn is equal to the continuant with index n plus 1. And the variables in the parentheses are a's from 0 to n. But I will not write them down so that we do not have too much information on the board. You'll have to either believe me that everything will be okay or check it yourself. Q nth is equal to continuant with index n. At the same time, p with index n minus 1 is equal to continuant n of some of these a's, and q with index n minus 1 is equal to k with index n minus 1 of, once again, some of these a's. And in one of the other previous videos, we saw that these four continuants satisfy an equation. Let me remind you of this equation. K n plus 1 multiplied by k n minus 1. Well, we have some variables here and here, minus k n multiplied by k n is equal to, well, before I say what it is equal to, let me just emphasize that this and this are different continuants. Well, it is the same type of continuant, but variables in here and in here are different. So we cannot write kn to the power 2. It's not a square. It's just the product of two continuants. And all this is equal to minus 1 to the power of n plus 1. So gathering all this together gives us that pn multiplied by qn, actually pn multiplied by qn minus 1, minus p n minus 1 multiplied by qn is equal to minus 1 to the power of n plus 1. Why is this equation or just statement interesting? Well, if we take two neighbor convergents and try to calculate the distance between them, so Pn over Qn minus Pn minus 1 over Qn minus 1, we will have, well, let me write this completely, Qn minus 1, and over here we have Pn Qn minus 1, multiplication of these two, minus product of these two, minus Pn minus 1 multiplied by Qn. Well, it may seem complicated, but it's just a difference of two fractions. And we see that due to this equality, it is equal to minus 1 to the power n plus 1 over Qn and Qn minus 1. What is the meaning of this equality? Well, we understand that as greater n gets, the greater this denominator get. So while n tends to infinity, we understand that this denominator also tends to infinity with much larger speed than these denominators separately. So I believe that this means that convergence of the continued fraction become closer to each other. But let's take a look at their position on the real line. Say so A0 is just equal to P0 over Q0, and we understand that it is less than any other convergent. So we place P0 over Q0 here. And then, well, we already understand that P1 over Q1 will be somewhere to the right of this point. Well, to that direction. But let's take a look at this equality and substitute n with 1. So we have P1 over Q1, P0 over Q0. And if n is equal to 1, then we have an even number here. Well, this is an even number. So this is a positive number. So indeed, according to this equality, P1 over Q1 is greater than P0 over Q0. So let's place it somewhere here. And where is P2 over Q2? So once again, we rely on this equality and substitute 2 instead of n. So n is equal to 2. So P2 over Q2 minus P1 over Q1, well, this difference, is equal to minus 1 to the power of 3 over, well, something obviously positive. So this is negative. And we understand that P2 over Q2 is less than P1 over Q1. Okay, so it's somewhere here. But is it less or greater than P0 over Q0? Once again, we use this equality so that we can conclude that the distance between first and second convergence is 1 over the product of their denominators. And the distance of first and 0th convergence is 1 over the product of their denominators. But who has larger denominators? Of course, where we can take Q1 and Q2, this will be smaller than if we take Q0 and Q1. So P1 over Q1 is greater than P2 over Q2, but at the same time, the distance between them is less than the distance between these two. So P2 over Q2, it's somewhere over here. Using the similar type of deduction, we can conclude that P3 over Q3 is somewhere over here, and P4 over Q4 is somewhere over here. So these, and so on, of course. So these convergence form a very interesting sequence from 0 to 1, from 1 to 2, from 2 to 3, from 3 to 4, and so on. And we see that the convergence with even numbers increase, and the convergence with odd numbers decrease, because that is the direction of the real line. Does it follow from this that there is a limit of this sequence? Well, certainly there is a limit of even convergence, because they increase and they have an upper bound. Well, of course, there is a limit of odd convergence with odd numbers, because they decrease and they have a lower bound. But is there a limit to all of them? Well, of course, yes. And this happens because the difference between two neighbor convergents tends to 0. So from this, we can conclude that there is always a limit of all of the convergence. And this very point, this very number, is called the value of the continued fraction.